Assalamu alaikum. Welcome back to our series Science and the Quran, to part 3 of the story of sunshine and iron. We had left off at this impasse between geologists and biologists versus physicists and astronomers, with the best available theory being Helmholtz's theory of solar contraction, that the sun got its energy by contracting and that the kinetic energy of motion of its outer layers was what was powering it and allowing it to give off heat and light. But that would have meant that the sun had to be made of some different kind of matter than on Earth. All we have to study of the sun, of course, is not a piece of the sun, but just the sunlight, but it turns out that was enough. How? Well, again, let's look at the amazing journey that humanity takes, one scientist standing on the shoulders of another. In 1666, Newton, a man of many, many achievements, studied light and realized that when you pass it through a prism, it breaks up into different component shades, right? That's the phenomena of the rainbow that we're also familiar with when raindrops in the atmosphere act like a prism. In 1803, Thomas Young develops a spectrometer and actually is able to look at the spectrum of the different wavelengths of light that go into making white light or sunshine. Now, Fraunhofer, an optician, develops an even more accurate spectrometer and looks at the solar spectrum across the different wavelengths of light, long wavelength red light here, short wavelength violet light here, and Fraunhofer sees something amazing, that in the solar spectrum there are actually dark bands. Some of the wavelengths are missing from what was once thought to be a continuous spectrum that went from red to violet. How could that be? Are you intrigued? I am sincerely hoping that you are finding this as exciting as I am, and that we have not fallen prey to thinking that this sort of stuff is boring. This was an amazing intellectual journey of humanity. So the ball was handed off to Kirchhoff and Ångström. And what did Kirchhoff do? Kirchhoff realized that when you have a light source and you shine it through, say, a gas cloud, every gas would absorb some of that spectrum of light, giving a dark band, and its absorption spectrum was like a fingerprint. It was unique to that sort of gas. In fact, when the gas was heated, that wavelength is what it gave off, its own spectrum. Ångström then was able to study the sun spectrum, and here the jagged line is the spectrum of the sun versus the wavelength of light, superimposed on what a perfectly continuous thermal radiator that radiated in all wavelengths would look like. And here, the low points are the missing parts of the spectrum. And putting it together with the fingerprints about different gases that had been produced by people like Kirchhoff, Ångström was able to come up with an amazing conclusion, that the sun was made mostly of hydrogen and a little bit of helium. So finally the composition of the sun was discovered from its thermal spectrum. So then the puzzle became, how could a ball of hydrogen give off this sort of energy? People were entirely stumped. Now, another discovery comes to the rescue. It was the discovery of radioactivity that finally was able to reconcile the divide between the geologists and the physicists. And this discovery, again, one of humanity's most amazing, came quite by accident. The French physicist Antoine Becquerel, in 1895, discovered a completely new phenomena for humanity, the phenomena of radioactivity. he was studying one of the most complex atoms known at that time, uranium, and he noticed that they seemed to constantly be giving off radiation, be giving off energy, seemingly out of nowhere. No one had ever seen this sort of spontaneous generation of energy before. In 1901, Pierre Curie, and I'm sure you've heard of Pierre Curie and Marie Curie, calculated the amount of energy given off by a single radioactive atom and found it to be surprisingly large, for an atom, that is. So how could this happen? Humanity was now faced with an entirely new phenomena, energy that seemed to come out of nowhere. Well, as you can guess, Einstein and Rutherford come to the rescue. Rutherford discovers the structure of the atom. He discovers that the atom is made of a central nucleus, which is in turn made of nucleons, protons, and neutrons, with electrons orbiting around them. The protons are positively charged, the neutrons have no charge, and the electrons are negatively charged, and their negative charge balances the positive charge of the protons. So, through a series of very ingenious experiments, Ernest Rutherford uncovers the internal structure of the atom. Einstein, of course, in 1905, with the special theory of relativity, had given humanity E equals mc squared, that energy and mass were interchangeable. And so, it was discovered that radioactivity was precisely this process where some of the mass of an atom was converted to energy. So let's take a look at the uranium atom, which we have been talking about. Uranium decays spontaneously. The reason it gives off energy is it is unstable, and it changes, it splits to helium and thorium. And the thorium goes from an excited state to an unexcited state, and energy is given off. Now, the energy for one decay, one atom, is about 4.3 million electron volts. That's small by our measures, believe it or not, but it is very big for an atom. And the amazing thing is that the half-life of uranium turns out to be 4.5 billion years. If you have a pile of uranium, it would take 4.5 billion years for half of it to be converted to thorium. So this seemed like it could be the key to unlocking how the sun could radiate energy and how it could do it steadily for so long. Now, here's an important side note for those truly interested in science among you. The uranium atom has 92 protons and 238 total nucleons, meaning 238 minus 92 neutrons. If we look here, we look and see that the number of nucleons actually stays conserved. 90 protons plus 2 is 92, and 234 plus 4 is 238. So it would seem that the total number of protons and neutrons hasn't changed. So how could the mass change? Well, again, it turns out that mass, remember, is interchangeable with energy, and a lot of the mass of a proton and neutron is tied up in what's called its binding energy in the nucleus. And so, amazingly enough, when you weigh this and you weigh these two and add them, these two weigh less than that, even though the number of protons and neutrons are conserved. And that difference in mass, when it is plugged into Einstein's equation, E equals mc squared, is exactly the total energy given off by this decay, in the kinetic energy of the particles, in the gamma rays, and so forth. And so now, the puzzle began to unravel, that the secret to the sun must be radioactivity. Now here's an important sidebar, because you may think, what's the big deal? We burn wood or coal here on Earth, we end up with some ashes, and we've converted the mass into energy. That's actually not what happens at all. When we burn wood or burn coal, all we are doing is rearranging chemical bonds, but we are not changing the nuclei as we did with uranium, where the nucleus itself changes to something else. So in this case, we can say that no mass is converted to energy. E equals mc squared is not active here. And this experiment has actually been done many times. If you take the mass of the wood, the mass of the oxygen that fire needs, you measure the mass of the carbon dioxide and water vapor, and the mass of the remnant ash, the masses before and the masses after are exactly the same. There is no change in mass. The energy is extracted from stored chemical potential energy in the bonds inside the wood. That would be maybe a little bit easier to understand if we look at another process we're very familiar with, which is how we absorb energy from our food. This molecule, C6H12O6, is glucose. And we do the same thing in our body, but in a much more controlled way. We burn the glucose with oxygen, and we convert C6H12O6 plus 6 atoms of O2 to 6 atoms of CO2, carbon dioxide, and six molecules, of carbon dioxide and 6 molecules of water. So we take 1 molecule of glucose, 6 molecules of diatomic oxygen, and we burn that glucose just like the burning of wood, but in a much slower way. And what we get out is 6 molecules of carbon dioxide and 6 molecules of water. And if you add up all the carbons, oxygens, and hydrogens, you see that they are the same on both sides of the equation. But that is why we need oxygen. If you've ever wondered why do we need to breathe oxygen, it is to allow this process to take place. And its products are water, carbon dioxide, and energy. And that, by the way, is why we breathe out carbon dioxide. And the energy comes from chemical potential energy stored in wood or in food. And what is the source of that chemical potential energy? You guessed it, it is the sun. And so, burning of wood, burning of glucose is releasing energy that is stored in chemical bonds. It is what is known as an exothermic reaction. So during an exothermic reaction, the reactants have a higher stored level of chemical energy than the products. Glucose and oxygen have a high level of stored chemical energy. Carbon dioxide and water have a low level of stored chemical energy. And that difference in energy is what is released in the heat and the light of a wood fire, or in the energy in our bodies, which is carried by a molecule called ATP. So combustion reactions then are exothermic, where a substance burns, combines with oxygen, and releases energy, typically for a fire, for example, in the form of heat and light. And all what we're doing there is breaking some bonds and rearranging them, but the carbon stays carbon, the hydrogen stays hydrogen, the oxygen stays oxygen. No changes are taking place in the nuclei. So let us end then this session by pausing a minute to look at the miracle of fire and food, which is the release of stored chemical energy. So let's look at the summary from a physics website. Burning and other changes in matter do not destroy matter. The mass of matter is always the same before and after the changes occur. The law of conservation of mass states that matter cannot be created or destroyed, and that is for the most part true, and certainly in this case we consider it true. Now, in Surah Al-Waqi'ah, Allah subhanahu wa ta'ala asks us, أَفَرَأَيْتُمُ النَّارَ الَّتِي تُورُونَ? Have you ever considered the fire which you kindle? أَأَنْتُمْ أَنْشَأْتُمْ شَجَرَتَهَا أَمْ نَحْنُ الْمُنْشِئُونَ? Is it you who have brought into being the tree that serves as its fuel, or are we the cause of its coming into being? And now we understand something about how amazing this process is. Something had to give wood and glucose and coal the sort of structure where the chemical bonds in it have a high stored chemical energy and allow it to react with substances like oxygen, where the products then have a low level of stored chemical energy, and then energy can be released. We as Muslims believe that this was not an accident, that this was a product of design. And when Allah subhanahu wa ta'ala asks us, have you ever looked at the fire that you kindle? Are you the ones that have stored this chemical energy in it? Are you the ones that have made the tree that serves as its fuel? Are you the ones that have designed this system? Or are we? I hope now we can appreciate those verses in a new light. And let's just pause at one subtlety of the Arabic. Have you ever considered the fire that you kindle? Let's look at this. We're saying that with wood and oxygen, the reactants are at a higher level, and so they will want to release energy and form products at a lower level. This reaction is a favorable reaction. It's called an energetically favorable reaction. We don't have to put energy in to make it happen in theory. But it turns out that we actually do have to put a bit of energy in. Why? Well, you know that. You know that if you put a log in your fireplace, it won't spontaneously combust. You know that if you live in a log cabin, thank God it doesn't spontaneously begin to burn. We have to put in some energy to break these chemical bonds, whether in cellulose that makes up wood or in glucose that we use in food. And once we have put in some energy to get the process started to break these bonds, then they can combine with oxygen and form new molecules like carbon dioxide and water. And so the fire actually needs to be kindled. And that, of course, is also a very important thing for the stability of our life here on Earth, because obviously, if forests burn spontaneously, rather than occasionally when they're struck by lightning, or wood spontaneously combusted, or the food in us spontaneously combusted, that would be a big problem. And so indeed, it is a point of great finesse where Allah subhanahu wa ta'ala is saying, have you considered the fire that you kindle? Have you set up, have you brought into being its tree? Or are we the ones that have done that have set it up as an exothermic system, but one that requires some input of energy to get started? And not all chemical reactions are like that. Many of them don't require an input of energy. They will proceed immediately, spontaneously on their own. But in this particular case, thankfully, it does not. So thank you for paying attention to this long session, and I hope that you have found this illuminating. We will see you next time then when we get back to our puzzle of sunshine. Assalamu alaikum.